So we'll go ahead and start with these. Now, if you have more questions, we can add them to the list. But we'll start with question 3 out of 4. Okay, so question 3 is talking about the Richter scale. Now, when we talk about the Richter scale and the decibel scale, they are ratios. So on the Richter scale, it's a measure of how powerful that earthquake is compared to the normal movement of the earth. How many times more powerful? And it's by a factor of 10 because logarithms are 10 times as much. So when we look at this, this is going to be our formula. Log of I over I naught. Okay, so let's go ahead and read through this one. An earthquake was recorded with an intensity of 125,893 times more powerful than the reference earthquake, or that times I naught. What is the magnitude of this earthquake on the Richter scale? The Richter scale is this. So we're going to find our Richter scale measurement, and that is log. Now, I don't write the 10 because we understand that if there's no number there, it is base 10. So it's just a log of I over I naught. Now, when we plug our values in, we are looking at 125,893 times more powerful. So that's going to be that times I naught over I naught. Now, what is I naught? I naught is just the movement of the earth on its own. The earth is always constantly moving, so it's just the value of that. This is referenced to just the normal shaking of the earth. Earth always shakes, it always is in movement, so it's just the initial part. So this is quite a bit larger. Now, what's going to happen with the I's? They do what? I naughts, they cancel. And that leaves you then with simply the log of 125,893. And we can use our calculator to directly solve this out, can't we? We can use our calculator to directly solve this out. And we just use our log key in the calculator. So 125,893. We'll take the log of that, and we want to round it to one decimal place. So on the Richter scale, that would be 5.1. So it's 125,893 times as powerful, but it's only a 5.1 on the Richter scale. Right? And so Richter scale, a large change is represented by a small change because of the use of the logarithms. Okay. Question 11. So let's see what we need to do for question 11. Suppose that the salinity S of the ocean water is given by its depth is modeled by this equation, where S is measured in grams of salt per kilogram of water, and D is a distance in meters. What is the salinity when the depth is 931 meters? So the salt content of water changes with the depth. So we have a formula here, and we're just going to have to plug in the values. So we've got S of D, that's the salinity, and this is question 11, by the way. So we're looking at S of D, and S of D is 31.7 plus 1.5 log of D plus 1. Right, so the depth plus 1. Now we want a depth of 931 meters, right? So it's in meters. So we're going to use D equals 931. We're going to plug that value in, and we're going to calculate it out. That's going to require us to use our logarithm. So let's see what we have. We've got 31.7 plus 1.5 log of 931 plus 1. So that's the log then of 932. Okay, we're going to add those together. And let's use our calculator here. Now, you can actually type it all in at once if you want to. You can break it up in pieces, or you can just do it all at once. We have a calculator here, so let's do it all at once. So we've got 31.7. Okay, we're going to add to that 1.5 times log of 932. And that gives us then a final answer of 36.154. And we want to round this to the nearest hundredth. So tenths is 1, hundredths is 2. So we round this to the nearest hundredth, and it looks like it's 36.15. Yeah, 36.15. And that is going to be in terms of grams of salt per kilogram of water. And the salt content of water changes again with the depth. And the deeper that you go, the saltier the water is, the higher the salinity is. Not by much, but it does change. Did we have any other questions out of 4.4 to look at? So we did question 3, and we did question 11. Did we have any others out of 4.4 to look at? Anybody else have any other questions? Which one? 7. Sure. Yep, we can look at 7. And 7 is a population model. Logarithms and exponentials can be used to model populations. So over time, a population is either going to increase or decrease. The population growth of an animal species is described by this equation, where t is measured in months. And we want to find the population of this species in an area 6 months after it was introduced. So we want to figure out what it would be 6 months from now. So this is the equation that we're going to be using. And it's just a matter of plugging the values in. So we've got f of t equals now 400 log of 2t plus 3. And we want 6 months, so that means t is going to now be 6. So that's what we're going to be using. So we're going to be using t equals 6 here. So let's plug our values in. Break it all down. And 2 times 6, that's 12, plus 3 more makes it 15. And how do we solve this out? We've got it all here. Now, all this is a calculator problem. So that's all we need to do is just type it in our calculator from here. Plug the values in. We just simply type it in. So we have 400, right, times log of 15, and that gives us now 470.4. Well, we'll go ahead and round to the nearest whole number because we're looking at population. Can't have half of an animal, so it looks like we're going to have 470. So that population should be 470. And again, I just rounded to the nearest number, whole number, because you can't have half of an animal. So the answer on that one would be 470. And you can label it as 470 species if you wanted. Is everyone okay with how I did that? So just use your calculator and plug it in. Are there any others out of 4.4 to look at? Anything else out of 4, 4? No? Okay. Now, 4, 5 is the trickier section. We started it a little bit last time, and we're going to finish it today. And some of these questions are a lot more difficult to solve than others, and they require different techniques. And so they do require a little bit of thinking outside of the box. So we're going to go ahead now and look at question number 2 out of 4 or 5. And each one of these can be solved in many, many different ways. You can use the properties of logarithms, exponentials. But when we look at this, our goal is going to be to make sure the logarithms are all on the same side and make sure those logarithms are combined into one logarithm. That way, I can get rid of the logarithm by using the power of 10. So the first thing I'm going to do, hey, no problem. We're just looking at 4.5. We're looking at question number 2 from the homework here. And we want to solve this one out. Now, again, what is our goal? Our goal is to somehow get this into one logarithm. Because then once it's inside of one logarithm, I can remove the logarithm with the power of 10. E gets rid of a natural log, so E gets rid of an ln. Power of 10 gets rid of a log base 10. Power of 5 would get rid of a log base 5, and so on. So let's go ahead and move that log of x over. This gives us now this. We want to try to combine this into now one logarithm. Logarithms have some unique properties that only logarithms use. And these properties we talked about a little bit last time. But I'll go ahead and put them up on the screen. And these properties were all explained in 4.3, I believe it was. Let me find those properties. On page 469, these properties here. Question 3? Yeah. Should be 5.1. We just did that. Yeah, is that the one you're looking at? Okay, I'll leave that up on the screen for you to copy down for a few seconds. Okay, but let's go ahead now, and while we're talking about that, while we're working on that one, when we talk about logarithms, logarithms have some unique properties. All right, logarithms, you could take multiplication and split it up into addition of 2 logs. Or you can have division and you can split it up into subtraction. Now our goal is going to be combine this into one logarithm. So when I see this, I want to get it combined into one logarithm. Now our properties are on page 469. And our first property says this. When I have 2 logs added together, I can convert that into one log with multiplication, right? And a lot of times we want to get it into one log. So you may have to split them up or combine them together. Logs are unique because multiplication becomes addition and division becomes subtraction. So let's go ahead and put these together with our properties of the logarithms. So these can go together as multiplication, right? Right now it's addition. So I can rewrite this as the log of x times x plus 3 equals 1. Now, why did I do that? I did that because I can now eliminate the logarithm. And the logarithm is log base 10. So how do I get rid of a log base 10? I use the power of 10. And whatever I do to one side, I have to do to the other. When I use that 10, that is going to cancel out that logarithm. So that logarithm is, again, log base 10. We don't put the base there, but we know it's log base 10. So that goes and that goes. Now that leaves you then with x times x plus 3. And what about 10 to the first power? 10. Now the logarithms are all gone, and now we can proceed to work with this equation. So what would we need to do? Well, eventually we've got to set this equal to what? 0. Before we can do that, though, we need to distribute that x through. So we'll do that. We'll go ahead and distribute that x through. And that's going to give me then x squared plus 3x equals 10. We'll move my 10 over, and then we can factor. So now we've got x squared plus 3x minus 10 equals 0. And first times the last is a negative 10. Okay, and what do we know about the signs? Are they the same or are they different? Different signs. And the sign in the middle is positive. So what two numbers are going to work here? Okay, 5 and 2. Positive 5, right? And a negative 2. So that then factors into x plus 5, x minus 2, and that equals 0. Okay. And that gives me then x equals a negative 5, and x equals a positive 2. Now, what can we not do? We cannot put a negative, take a negative of a logarithm. So when we go back up and we look at our original, and so I'll move this back down in a moment. When we look at our original, way up here, this is our original here. What happens if I plug in the negative 5? If I plugged in the negative 5, can you take a log of a negative 5? No, because if you try it in your calculator, what's it going to do? If you try to take the log of a negative number, right, there's our log. If we try to take log of a negative 5, look what it gives you. It gives you a domain error, right? Doesn't work. So we cannot use the negative 5. Why not? Because it would make you take the log of a negative number. And that doesn't exist, so that one will not work. And why does it not work? Because that would make you take the log of a negative number. So we cannot take a log of a negative number. But we can take 2, right? Because log of 2 works. And 2 plus 3 is 5. And we can definitely take the log of 5. Okay, so do we kind of see how we would approach that question? And some of these require all kinds of different techniques. We're going to learn many, many different techniques for solving these. Did we need to do another one out of 1 through 3? 3? Okay. Let's think about how we would look at question 3. Question 3 is log base 9. So it is a little bit different. Of x minus 5 plus log base 9 of x minus 5 equals 1. Now we're going to use the same technique that we just applied a moment ago. What are we going to do? We have logs that are added together, so those can be combined into one logarithm. So I can rewrite this, and we could use different properties to solve this out. I'm just going to go ahead and combine them together, and then we'll take our square root after we do all of that. So let's combine them together into x minus 5. And you could even write it as x minus 5, so quantity squared, doesn't matter. But it's a multiplication here. and that still equals 1. Now, how can we get rid of this one? This one's a little bit different from the last one. All right, the last one was log base 10, right? This is log base what? 9. So, let's go ahead and take both sides to the 9th power. That will cancel out that log base 9. And I'm going to go ahead and rewrite this now as, when I rewrite it, those can cancel. And I'm going to rewrite this as x minus 5 quantity squared. And it equals 9. We do not have to FOIL all of this out because we can solve this directly. What would we do to finish this one out? Square root, okay? We don't have to FOIL it out. We don't have to do anything else, right? We can directly use the square root property. And whenever we take a square root, what does that induce? Plus or what? Plus or minus. So make sure you're careful with that. So when you take that square root, make sure you add on that plus or minus. And what's the square root of 9? 3. So that's going to give you now x minus 5 equals plus or minus 3. Go ahead and get your two possible solutions, I should say. So we've got x minus 5 equals positive 3. And so move that 5 over. And so one possible solution is x minus 8, isn't it? Okay, let's check the other one. What's the other one going to be? It's x minus 5 equals a minus 3. We'll add our 5. And that's going to give us x equals 2. Now, one of these is probably not going to work. 2 is not going to work. Why is 2 not going to work? Well, 8 will work because 8 minus 5 is 3, and I can take the log of 3. 2. 2 minus 5 is a minus 3. Can you take a log of a negative 3? No. So, 2 does not work. So, the only one that's going to work is going to be what now? 8. Is everyone okay with how I did that one? 2 and 3 are very, very similar. It's just that it uses a different base. And you always use the same power as the base to clear it out. Okay, now let's work with some more of these. They're all a little bit different, and these are all going to require slightly different techniques to solve. So we'll now look at one that's an exponent, and we'll see how to handle one of these. So we'll find a couple from our textbook to look at. And again, they're all a little bit different. We're going to go through several different types. Each type is solved in a different manner. Okay, we're in 4-5 here. So let's look now at question number. Question number, we'll just pick one of these. How about question number 17? And this is on page 496. So page 496. We're going to look at question 17. Okay, so we're going to look at these. And we're going to try to get this to the nearest 1,000. And that equals 3 to the 2x power. Now, what we cannot do is we cannot get the bases to be the same, right? Because we have a 4 and we have a what? 3. So what we can do is we can use a logarithm. Now, why would I want to use a logarithm? Well, going back to our properties, if we go back and we look at our logarithm properties here, you will see that there's one for powers. Okay, logarithms have many, many special unique properties. And one of them is that we can bring down the power. So if we look at our logarithms, okay, when we talk about logarithms, if we have a power, we can bring that power down. And that's going to be a technique that we're going to be using. Now, you can use ln or you can use log base 10. It doesn't matter. Most of the time I'll use log base 10, but you can also use the natural log. So what I can do is I can take log of both sides. Whatever you do to one side, you have to do to the other. Now, when I take a log of both sides, then I can apply the property that says this can come down, and so can this. So powers can come down. So that is now going to leave me with, when I bring that power down, that is going to leave me with something that I can work with. So I'm going to go ahead and bring that power down. And rewriting, that's going to be, let me find a pen that works right here. Switch those out. Okay, so bringing that power down, let me get a pen that works. Bringing that power down, that gives you x minus 1 can come down, log of 4 equals 2x log of 3. Now, what we want to do is we want to now solve this for x. Okay, so we're going to have to move things around. We're going to have to get the x by itself. So the first thing I'm going to do is I'm going to go ahead and distribute this log of 4 through. So that's going to now give me x log base, log base 10 of 4 minus log of 4 equals 2x log of 3. Okay. Now we have to figure out how we can solve it from here and what we can do. We need to eventually get this to the point where we can solve it. We need to go ahead and get the x's together so we can factor it out. So let's see what we can do. Our goal again is to get all the x's on the left-hand side. So I'm going to move that 2x log of 3 over so it can join the other one. And I'm going to have to also add on that log of 4, so that'll move over. So now we have x log of 4 minus 2x log of 3 equals log of 4. Okay, now we can factor it and we can solve it. So we still have to do quite a bit of work, but now it's calculated. Okay, we can now factor out that x. And when I factor out that x, that's going to leave you log of 4 minus 2 log of 3. And that equals log of 4, right? I just factor the x out. This is now going to be all calculated. So let's go ahead and work out all the different pieces here. And we'll break this down. We'll use our calculator to get this side. So let's work on this. Okay, so I'm going to try to do all that. You can do it at once, or you can use a piece of paper, write all the pieces down. Again, just do it all at once. I'm probably going to do it all at once. So we're going to take log of 4 minus 2 log of 3. And that is going to come out to be, now when I work it all out, a minus 0.3522 if you round x. And let's look at the other side. What's the other side? It is simply log of 4. All right, and log of 4 is 0.602 if we round 1. We can now divide, and we can get our final finished answer. And we want to now round to the nearest. Okay, for these, for 11 through 34, give the solutions as a decimal, correct the nearest thousand. So tenths is 1, hundredths is 2, thousandths is 3. So we're going to divide those out. So 0.6021. We're going to divide that by a minus 0.3522. And that's going to give me then, if I round, a minus 1.7. Let's see here. It looks like if I round 20, close enough. Because that would round out. And that would give you minus 1.72. Oh, wait, did I make? Oh, it should be 7-1, shouldn't it? Yeah, my mistake. It should be 7-1. Sorry about that. I do what now? Yeah, I can move it up. And that was, I just wrote it down. It should be minus 0.71. So let's review what we did. Different ways of solving these. The way I thought about it was, I can use a property of a logarithm. Why do I use logarithms? Because logarithms have some unique properties. Addition becomes multiplication. Subtraction can become division. Also, powers can come down. So I want to get that x to come down. So I'm going to take the log of both sides. So that's what I did. Right? I took the log of both sides. Now, that then allowed me to bring down that x minus 1 and bring down the 2x. Then what I did was I said, let's get all the x's together on one side so we can factor it out. So that's what I did. Then I moved the 2x log 3 over, and I moved the log of 4 over. That then gave me this. And once I was here, I said, well, I can factor an x out of all of that, which I did, and that's what we want. We want to get the x by itself, so I factored it out. This was then nothing but pure calculator. So I just did all of this in my calculator, and I got that minus 0.3522. And then log of 4 is 0.6021. And then I simply divided, and I divided all that out on both sides, and I rounded to the nearest thousands, which would be 3 places. And when I did that, see, it came out to be that, right? And if I round to 3 places, that 5 will make it round up. So that'll be a minus 1.7. It should have been more careful. 7-1, not 2, just the way I wrote it. So is everyone okay with what I did there? So logarithms have those unique properties. Powers can come down.
Why did you put the log 4 in the output, like in the 4 line?
Okay, which piece? Okay, so do you see where I got to here, right? Okay, and then I got to here. Are you going up or down?
Down.
Okay, yep. Okay, so we're okay with this step, right? This step. Where this came from? Okay, this came from when I distributed this log 4 through. I just have x log 4 here, and then I have a log of 4 times a negative 1, and that's where that came from. So I just distributed that log back through, because I had to do that in order to get all the x's by themselves. Again, these can be tricky at times, and they require you to think a little bit outside of the box. All of them are a little bit different from each other, and they require different techniques and different ways of thinking. They're like the questions that we did out of 1-7, I believe, where they were 1, 6, and 7, where you had to think about how am I going to solve it. You might have to use some substitutions. You might have to square and then get rid of things. Kind of similar to those type of questions, where you have to think outside of the box a bit. Let's do another one. Similar to it. Let's look at, how about we look at a question that has an E in it. So how about question 23? And this is page 497. This one was 496. Yep, no problem. Okay, so question 23. We've got e to the 3x minus 7 times e to the minus 2x equals 4 e. Okay, so this one is exponentials instead of logarithms. And they, again, require some different techniques and different ways of thinking. Now let's think about exponentials and how they work. Remember this fact about exponentials. A to the n plus a to the, let me write right here. A to the n times a to the m, we can rewrite that as a to the n plus m power. Remember how that works? Because when you have multiplication and they're the same bases, what do the powers do? The powers are going to add. Okay, these happen to be the same bases. So that's going to be e to the 3x minus 7 minus 2x. And that still equals 4e. Okay, let's clean it up a little bit. And I can combine these together, and that then gives me e and a 3x minus 2x. That leaves you with an x minus 7 equals 4e. Now, what we can do is we can get rid of that e. Logarithms and exponentials are opposite of each other. So if I had a log base 10, right, I used a power of 10. Or if I had a power of 10, I'd use a log. Well, this is an exponential to e. And what's the opposite of e? The natural log. So how do I get rid of an e? I'm going to use an ln. So let's take the ln, the natural log of both sides. And we're just going to slowly break it down until we can get to a point where we can calculate it out. So the e and the ln, those can cancel. And so this side is an x minus 7. And that equals the ln of 4e. Okay, because the natural log and the logarithm went away. And I can combine these together. Why can I put these together? Because when you multiply, exponents add if they have a common base. Now what can I do? Well, let's make sure I didn't copy anything down wrong. I believe it's all right. Okay, yep. Okay, so this is what we started with. Right? And then these can go together. Now, why can these go together? Yep, I copied it all down, right? These can go together because exponents add. But that's a minus. So that's why it becomes a 3x minus 7 minus 2x, because it's minus, right? It just comes along with it. So those put together because the exponents can add together. And that exponent was negative. So those go together, and that gave me that. Now, what can I do from here? Well, remember our properties of logarithms. This is log multiplication. So I can split this up into the natural log of 4 plus the natural log of e. Okay, so this and this canceled, right? But this won't cancel here because this is a whole quantity. Right, but what we're going to do is this is a product, so I'm going to split it up. Now, this right here, the reason why I split this up is the natural log of e is 1. Remember that? Natural log of, or log of 10, when you have log base 10 of 10, that's 1. Log base 9 of 9, that's 1. Natural log of e is 1. So that then gives me something that I can work with. So now we have x minus 7 equals a natural log of 4 plus 1. I'm going to go ahead and move that 7 over with addition. And that leaves me now with x equaling the natural log of 4 plus, when I moved it over, 8. And now I can break it up, and now I can finish it. Because I can do the calculator to calculate all of this down. And we wanted to, in this case, calculate it down to 3 places. So let's go ahead and do that in our calculator. We now have something that we can work with. Right? Took us a little bit to get there. We want the natural log of 4 plus 8. Make sure you close the parentheses there too. Make sure you close the parentheses. So natural log of 4 plus the 8. That gives us then a 9.386 if we round. Okay, and that should be our answer. Does everyone see what I did? And you could have done this in your calculator up here. I chose to break it down, but you could have actually done it in your calculator like this. Okay, you could have, it's a little bit complicated. I just break it up, but this here could be done as this, 4 second ln of 1. And it would give you the same thing. And then you could just add that 7 to it, and you get the same answer. Okay, I usually just break it up and use the fact that natural log of e is what? 1. That makes it easier. That way you don't have to plug in an e to the first power. But it'll give you the same answer if you use your calculator with the e instead of splitting it up. So that one was a little bit tricky because we had to use different properties. Now let's look at another one. And let me find one that's not going to be too terribly difficult. 36. This requires another new technique. And okay, this one, question 23, this went with questions 4 and 5. Okay, so 4 and 5 are like the last two. So question 36, this one is going to be like number 6 in your homework. And we're going to have to use, we can either factor it directly or we can use a substitution. And if you go on and you take a calculus course, you will use a lot of substitutions. It's all about substitutions. It's all about what we're learning today with substitutions. Not the logarithms, exponentials, but the way we solve them. They require a little bit of thinking. Well, what I can do is I can rewrite this as this, okay? Because this is an exponent, I can rewrite this as e to the x, quantity squared, minus 8 e to the x plus 15 equals 0. Why did I do that? Well, let's think about what we have. How many terms do we have? We have 1, 2, 3. Okay, this is a trinomial, and we can factor it. But let's use a substitution so we can see a little bit easier how it works. I'm going to let u equal e to the x. This is a common substitution that we can use. And if I replace that e to the x with a u, then I get u squared minus 8u plus 15 equals 0. And that, we should now know what to do. This now can be what? Factored, right? It turned it into a polynomial that we can factor, and then we'll substitute back. But this is something that we use a lot in calculus, is substitutions. So if you go on and you take a calculus course, whenever you take derivatives and integrals, you'll be using a lot of substitutions. It just makes it cleaner. It makes it easier to work with. So first times the last is a 15. What two numbers? Give me the 8 here. Okay, minus 5 and minus 3. So that factors into u minus 5. U minus 3 equals 0. So we've got u equals 5, and we've got u equals 3. Now, our original question here at the very beginning, did it have any u's in it at all? No. So what we now need to do is resubstitute back in that e to the x so that we can finish it out. So let's go ahead and resubstitute back what that u was defined to be. U is defined now to be e to the x. So how would I handle this? If I've got u equals 5, that u is actually e to the x. How would you handle this? How would you get rid of the e? What would you use? Can someone tell me? What gets rid of an e? Log. Yep, natural log, right? ln. So ln of both sides. So now we have it as x equals now natural log of 5. That's one solution. You can break it down. It says keep it as an exact solution. So you can either keep it like this or you could break it down. 3 places will be enough. Natural log of 5, and the natural log of 5 is 1.609. Close enough. So there's that piece. And what about the other one? Well, the other one was u equals 3. That means e to the x equals 3. And how do we get rid of that e again? We use what? ln. ln gets rid of an e. And that leaves you now with x equaling the natural log of 3. And so x equals now, on the other one, x is going to equal that 1.099. And it says keep the exact value. You can keep the exact value, which is here, or you can break it down. But we had to use a substitution on that. Yeah, both of these are correct answers. Right? We don't have to worry about checking them because our original had an e, an exponential. And you can take negative e to negative power all the time. You just cannot take a logarithm of a negative number. But you can take an exponent of a negative number. You just can't take a log of it. So let's try another one to look at here. A little bit different on this one. This one the other class struggled a little bit with. 54. This is a good review. This question takes a little bit of time to go through. And it requires us to use factor by grouping. And we may have forgotten that. But that's something that we have to do once in a while. This is what we want to solve. Now, is it already put together as one logarithm on the left-hand side? Yes, it's all combined together, so we don't need to split it up. Okay, now this is not just a log base 10. This is a log base what? 4. Okay, so how do we get rid of a log base 4? We use what power? 4. So we're going to take both sides to the 4th power. That 4 and that log of 4, well, they cancel each other out. So the left-hand side comes down to now be 3x plus 8 times x minus 6 equals, now what is 4 cubed? Okay, 4 squared is 16, right? So 4 cubed would be 64. Now let's see if we can remember how to solve it from here. What do we need to do? What is my next step here? Don't even worry about this logarithm. How would you solve this? What would you do? If I gave you this right here and I said solve it, what would you do? FOIL it. Okay? Yeah. Just so you remember, the other class they forgot to work this one out. You're going to have to FOIL it first, and then what are you going to have to do? Set it to 0, right? Set it to 0 and then refactor. Yeah, the other class forgot that's something you have to do. You have to FOIL it first. So let's go ahead and FOIL. Okay, so FOILing it out, we get 3x squared. We get a minus 18x. We get a positive 8x. And we get a minus 48 equals 64. Now we're going to combine like terms and we're going to have to factor eventually. This one is going to make us factor by grouping. So I'm going to move that 64 over. That 18 a negative 18x and that positive 8x, those go together. So now we've got 3x squared, we have a minus 10x, and we have a minus 112, and that equals 0. You've got to factor. And this one's designed to be, it will factor, but it's going to have to be done by grouping. And I picked this one on purpose so we would remember how to do factor by grouping, because there's a couple of questions on your final that either have you use quadratic formula or factor by grouping. So what do I need to do? It's already set to 0. I need to take the first number and multiply it by the second number. And that gives me a minus 336. What do I know about the signs? Are they the same or are they different now? They are different. And which one's going to be larger? Negative, isn't it? Okay. Now, what do we know about 336? Is it an even number or an odd number? It's even. So let's start with some different numbers. And it's a pretty big number, so let's start with 12. 336, we're going to divide that by 12. If I use 12, that's 12 and 28. But that doesn't work, does it? So let's go up a little bit, because that's pretty close. 12 and 28. See, that's a difference of 16, but we need what? 10. So let's go up a little bit more. Let's try 14. And that's the next number I'd probably pick is 14. Well, 14 and 24. Does that work? Yes. It does take a little bit of time to remember how to work these out. Can I jump directly to my factors now? No. I am going to have to do factor by grouping. Why? Because of that 3. So remember factor by grouping. They have to split the middle up. I know we did this back in chapter 1. That minus 10x, we have to split that up. So now we have a 3x squared. We have a minus 24x, a 14x, and a minus 112 equals 0. Almost finished here. What do we need to do next? Factor by grouping. So what can I factor out of the first two pieces right here? Okay, it looks like I can factor out a what? Not a 7, right? But the 7 will be left over, but I can factor out a 3x. So let's go ahead and take out our 3x. And you're correct. That's going to leave you with an x minus 7 left over. And the next two pieces, when I look at those, always check to see if that number in front will go into the second one. Oh, 8. I don't know why I wrote 7. Sorry about that. I was thinking 21. Yep, should be. I've got a 24, so it should be an 8 there. The next two pieces, what can come out of there? 14. And that's going to leave you with the same. X minus 8 equals 0. Are these groupings the same? Yes. So now we have x minus 8 and 3x plus 14. That equals 0, doesn't it? And now, what are my two solutions going to be? Yep, x minus 8 equals 0, so x equals 8. There's one of them. And 3x plus 14 equals 0. So 3x equals a negative 14. So x equals a negative 14 over 3. I picked this one on purpose. Now, the homework ones are a little bit easier. I picked this one on purpose to get you used to factor by grouping again. Because there's a couple of questions on your on your final where you're going to have to factor. Right? And a couple of them are factor by grouping. So I want to make sure that we remember factor by grouping. That is specifically why I picked this one out. All right, so we've got a little bit of time left. I'm going to work out one of the applications. You're going to have to do the other one. So the answer is 8, and the answer is also minus 14 over 3. Because I think they'll both work, won't they? Well, let's go back up and look. Okay, minus 14 over 3. Let's see what that is in the calculator. I think they both work. Minus 14 over 3. Okay, that's that. Let's look and see. Okay, so there it is. If I multiply it by 3, add 8, that gives you that, right? So that's that piece. Okay, so then we've got that minus 14 over 3 again. Minus 6 from that. That gives you then that. But then when you multiply it by negative, see, it makes it a positive. So both of them actually work, don't they? Because when you plug this back in, it actually multiplies together and it makes it a positive. So both of them work. I thought both of them did. And they both actually give you that 64, because 4 cubed is 64. So they actually both work because that multiplication of that double negative makes it positive. We've got a little bit of time left. So I am going to work out one of the applications from your homework, and you're going to have to do the other one. So I'm going to do 10. I'll leave 9 for you to do. I think 9 is actually the easier one. So I'm going to work out question 10. Now, exponentials and logarithms are used a lot in population modeling. Because a lot of things go, as you might hear them talk about something grows at an exponential rate. Well, what does that mean? That means it grows at something like this, an exponential function. So let's look and see what we have here. We're going to do question 10. I'm going to leave question 9 for you to work out on your own. It's actually a little bit easier. Question 10. The population of country A in millions is modeled by this exponential equation. During the same time period, the population of country B is modeled by this. In both formulas, X represents the number of years. Assuming these trends continue, estimate what the population will be when the populations are equal. And we want to round to the nearest million. So we want these to be the same. And then we have to find it. And in this case, X represents number of years. So we're going to have to find it, get our number of years. All right, are we finished? All right, hey, thank you very much. You stay together. And make sure you turn in your take-home final sometime today. You're welcome. Thanks, Bruno. All right, and yep, those will work. Those, and thank you very much. And I'll have these posted in Canvas later on. Probably get them either today or sometime this week or next week. All right, thank you very much. All right, and you're going to turn in your take-home final this afternoon.
This is I want to talk about because I'm going to stay here the break. But I'm going back home like on the Monday.
Okay.
Can I give my things to my friend and he drops
Yeah, you can do it that way or you can get it in Canvas Services. But if you want to give it to a friend, that would be a problem.
Because I have some homework and I will do like all of them.
Yep. As long as I get them, I'll grade them for you. Okay, so you have to give it to your friend, he'll bring it to me, and then I'll get them graded. Okay? All right. And hope you did well. So let's go ahead now and finish this one out. Before I forget to, just a second here. Marcus, I've got your exam graded too. I already graded that and got it recorded. Here, Marcus, everything's been graded, recorded. You can see your grade in hands. But you did very well. So. All right, so let's now go ahead and work out that question 10. So question 10, we want these to be equal. So we want that f to equal that g function. And then we'll solve it for the x, and we'll plug x back in, and we'll get the population in millions. Okay, so that's going to be our goal there. Put these up before I forget. So that's going to be our goal, is to set these equal and then solve them for x and then plug the x back in to get the population. So we are looking at these two functions. And this is question 10 from the homework. Question 9 is actually a little bit easier, so I'll do the harder one. We want to set these equal, so 16.8e to the 0.0019x power equals 13.3e to the 0.0124x power. So this is what we've got. Okay, now how can we work this one out? What can we use? Well, we've got different techniques that we can work through. What I would recommend is a logarithm, and I would probably use a natural log because we have the e. Now we're going to use a logarithm. That's going to allow us to bring powers down. That's our goal, is to get those powers to come down. So I'm going to take the log of both sides. And if I take the log of both sides, then this power can come down, and this power can come down as well. So rewriting, we now have 0.019x natural log of 16.8e, and that equals 0.0124 natural log of 13.3e. So all I did there was I just simply brought it down. Okay, now we're going to go ahead and work out each one of these independently. We can use a calculator, or we can just break it up and work with it the way it is. Either way, let's go ahead and just work them over to the side. So I'm going to go ahead and just work these over to the side. So how would I work out the natural log of 16.8e? Well, the natural log of 16.8e, we're going to use a technique that we used earlier today. So I'm going to go ahead and break this down. And I'm going to break this down into the natural log of 16.8 plus the natural log of e. Okay. And, am I missing an x somewhere? Oh, yep, I am. Sorry about that. Well, I would have caught it later on. But we're going to do that now. What about natural log of e? Natural log of e is what? 1. So this becomes 1. And let's go ahead and get the natural log of 16.8. So let's go ahead and find the natural log now of that 16.8. So use our calculator, and we want the natural log of 16.8. And then we'll add 1 to that. And that is then, we'll take this out to 4 places. 3.821 if we round 4. So that's going to be 0.019x, and that's going to be then multiplied by 3.8214. And what about the other one? Well, we need to work this piece out. Okay, so that's natural log of 13.3e. We're going to use the same approach to break it down. So the natural log of 13.3e is the same thing as the natural log of 13.3 plus the natural log of e. Natural log of e is 1 again. And natural log of 13.3, using our calculator, ln 13.3 plus 1 is then 3.58, let's say 78. Close enough there. Okay, so let's go ahead now and get all this multiplied together, and then we'll see what we've got. Okay, let's make sure we didn't make a mistake anywhere. Everything looks right so far. Okay, we're going to have to try to solve this for the variable x. Okay, are we missing a piece here? Let's make sure something doesn't look right. Let me make sure, because something doesn't quite look right. Let me make sure I've got everything modeled out correctly here. Should have been able to do all of that. Okay. Because I think we may end up with something that gives me 0, and I don't want that. Let's make sure. Okay, let me make sure I've got everything right here. Because I could have used that, and I brought that power down. And I brought that power down. Let me make sure, because I think I made a mistake somewhere. Let's double check and make sure. Okay, so we have this. So the first thing I did was that. Okay, so that would have gave me that. And I could have divided. And let's just go ahead and okay, so that gave me that, that gave me that. Let's make sure we didn't make a mistake somewhere. I think everything is right so far, but that's going to give me 0. So where did I make the mistake at? Let's start over. I know I made a mistake somewhere. Sorry about that. It won't take me long to start over. I think I made a mistake somewhere. Let me rewrite it again. Sorry about that. And make sure that we're solving it correctly. Because I think I made a mistake. Because that would give me 0. And I don't want 0. So let's make sure we did it correctly here. So we want these populations to be the same. Or maybe it will be 0. No, because that wouldn't work either. Okay, so we want these populations to be the same. So we've got f of x and we've got g of x. Right? So, oh, I see the mistake. Okay. Sorry about that. I made a mistake with my logarithms and I wasn't careful. Sorry about that. Let me rework this one out again. I should have been more careful with the properties and made sure I was more careful. So we've got this, and I see the mistake now. It was my mistake on not being careful with one of the properties of e to the 0.0019x equals 13.3 e to the 0.00124x. Okay, and I should have been more careful. I can still use the same properties, but I made a mistake. I'm going to use the same ln, but I did write it incorrectly, and that was my fault. I should have been more careful. When I rewrite this, I can split this up, because this is one whole part here. So I can split this up into the natural log, and it was my mistake of not looking at it this way. Natural log of 16.8 plus the natural log of e to the 0.0019x. The other side is going to be the same thing. Natural log of 13.3 plus natural log of e to the 0.00124x power. That was my mistake of not splitting it up correctly, because the power only goes to this piece here, not the entire part. So split the multiplication up. Now what can I do? Now this can come down, and this can come down. And that was my mistake just for going through it too quickly. I saw I made a mistake, but we found it. So I can now write this as this. Because that'll come down. That'll still leave you with a natural log of e. And what do we know about the natural log of e? 1. So this piece is 1, and this piece is also 1 again. So now we've got this. Let's take the natural log of that 16.8. We'll write that down. Natural log of 16.8. Natural log of 16.8, that is 2.82 0.1314. Okay. And the other side, we're going to need the natural log of 13.3. So let's get it. And that is 2.5878. So that's 2.5878. Sorry about that mistake, but I saw it when I worked it through, and that's 0.00124x, right? Okay. What happened to the 1? Okay, this 1 is being multiplied by that. And so 1 times that, it goes away. And that was my mistake before, was I was treating it as one whole quantity, and I shouldn't have done that. I should have wrote it as a sum first, and then brought the power down individually. That was my mistake of not looking at it correctly the first time. Now we can solve it, because now we can just move things around. So I'm going to move that 2.8214 over. And I'm going to move over that 0.00124x. Okay, and when I do that, let's see what we've got. Be careful with these decimals. So 0.0019 minus 0.00124. Oh, wait, I got too many zeros here. Sorry about that. We don't need those extra zeros. It should just be 1 0 there. Yep, should look like that. My mistake. Make sure I didn't put too many zeros in there, because this one has 2, and this one has just the 1. Sorry about that. The zeros will get you if you're not careful. Okay, so let's go ahead and work that out. So we've got to be careful with these. So we've got 0.00. Just make sure you don't make a mistake. 19 minus 0.0124. You've got to be very careful with those extra zeros, because, yeah, we don't need, there's too many of them there. I copied it down wrong to begin with. So that gives me then a minus 0.105. (0.105x) on this side, and the other side is the numbers. So let's be careful with those decimals here. It's so easy to make a mistake with these decimals. So on the other side, we have 2.5878 minus 2.8214, and that gives you then a minus 0.2336, and we'll divide, and it looks like we're going to come out to be a whole number. We'll get the nearest whole number. And we'll see how close we are to a whole number. And that gives us our value of x. So let's divide that out. And negative, of course, makes that positive, right? So we're going to put it in there. Now that answer is going to be positive. And we'll say that's 22.25. That's probably going to be close enough. 2 places is more than enough there, I think, for this case. Now, that is not what we want. Okay, that is the number of years. So, what would the population be? Okay, this is the number of years. So, quarter of a year, we'll get to the nearest quarter of a year. Let's go ahead now and use this to find now the population. And we're going to round to the nearest million. So, we go back to our formula, and we'll just find f of that. So, we need to find f of 22.2. And that is going to be, when I plug my values in, 16.8 e to the 0.0019 times that 22.25. And that's just a calculator problem. 22.25 times 0.0019. That gives you 16.8 e to the 0.042275, close enough. And we'll take that then to the exponential, to the e of it, and work it out. So 16.8 times e So we can see what we've got here. It's hard to see, but we're just going to take this, work it out in our calculator, and get our final answer. 0.042275. And that gives me then, it looks like, it says round it to the nearest million. So it looks like if I round it out to the nearest million, it looks like it's going to be about 18 million. So that one's about 18 million. So at about 18 million is when the populations would be the same 22 and a half years later. And that one was difficult. 9 is not as difficult. I worked out 10 because 10 was the more complicated one. I gave you